Assalamualaikum warahmatullahi wabarakatuh. Ladies and gentlemen, my name is Ratna Kartikasari. I'm from Mechanical Engineering Department, Institut Teknologi Nasional Yogyakarta. Our research team is Angelil Philadelphianto Maitano from Institut Teknologi Nasional Yogyakarta. In this opportunity, I will present my paper with title Microstructure and Wear Resistance of FEAL-MO alloy after deep cryogenic treatment. Okay, I will start with my slide. Cryogenic technology plays a major role in future technological advances. Cryogenic-based technologies have application in various fields such as metallurgy, chemistry, petrochemical, medicine, agriculture, food processing industries, etc. Materials for cryogenic applications must be chosen carefully because they will undergo drastic changes in their properties when exposed to extremely low temperatures. Excellency of DCT are free internal stress and retained austenites improve mechanical properties. This is due to all the austenite being transformed into martensite, removing residual austenite, finely dispersed carbide deposits, and residual stress loss. Disadvantages of conventional heat treatment are residual stress and retained austenite. The 300 series of austenitic stainless steel are widely used for cryogenic applications because their high strength and toughness at low temperatures. These alloys generally contain chromium 18 to 21% and nickel 9 and 14%. However, not all austenitic stainless steel can be used under cryogenic conditions because some austenitic stainless steels undergo structural changes from FCC and BCC at low temperatures so that they lose their ductility and toughness. Another problem with the use of austenitic stainless steel is the high cost of the element nickel and the limited world resource of chromium. At present, various efforts are being made by material engineers to find replacement alloys for expensive chromium alloys and nickel-based alloys. The FEAL-MN alloy is one of the innovations developed by material research in the world. My research aims to investigate the effect of soaking time in liquid nitrogen on the microstructure, hardness, and wear resistance of FEAL-MO alloys. In this research, we use method ingot are cut into the specimen for microstructures, hardness, and wear test. Then the DCT process was carried out in the nitrogen chamber for 1, 2, 3, 4, and 5 hours, followed by warming to room temperature. And then microstructure testing was carried out using scanning electron microscope and EDAs, hardness test using Vickers method, and wear test using Ogosi method. Our research, the first chemical composition of FEAL-MO alloy is Al 10.73%, mangan 15.35%, molybden 0.52%, and C 1.31%. This is microstructure result. In my research, this figure shows the microstructure of FEAL-MN alloy consisting of austenite, ferrite, and kappa structures, which are intermetallic compounds which surround the austenite grain. The dendritic pattern seems to dominate the microstructures of FEAL-MO alloy. After 1 hour of DCT process, where no changes have been seen in the microstructure at all. Furthermore, in the 2-hour DCT process, the ferrite phase began to enlarge and the dendritic pattern began to change orientation, although it could not be said to be significant. The same thing happened to the 3, 4, and 5-hour DCT process. The addition of 5 to 10% mangan to the FEAL-MO alloy system forms alpha austenite duplex structure. And then as results, the results of the test show the suitability of the composition of the elements in each phase. This is hardness result. The figure shows the curved result of the FAAL-MNMO alloys hardness test before and after DCT process. The hardness test results showed that the FAAL-MNMO had a hardness of 455 Ficker hardness number. This value is extremely high when compared to the hardness value of stainless steel 304 is 129 Ficker's hardness number. This is because formation of aluminum carbide and FeAl, which are extremely hard. After DCT process, there is a tendency to increase the hardness value. However, the increase in the hardness value is very small. The DCT process with 1 hour soaking time showed a minimal increase in hardness, about 2%, and the higher soaking time, the smaller the increase in hardness. This very small increase in hardness value is due to the absence of significant changes in the crystal structure during the DCT process. However, the value of hardness continues to rise with increasing soaking time. This is due to the rearrangement of the austenite and carbide grains. This figure shows that the wear rate of the FeAl-MnMO alloy is 0.0032 mm 3 per kilogram meters. This wear rate is quite low because the presence of elemental aluminum, which forms carbide compounds, and FeAl, alpha FeAl intermetallic compounds, which are hard. The DCT process reduces the wear rate, which decreases with the higher of soaking time. The 1 hour DCT process showed a wear rate of 0.003 mm 3 per kilogram meter. There was a decrease in the wear rate about 6%. The DCT process causes the release the internal stress and the reduction of microstructural defect, which are important factors in the increasing the wear resistance and strength of the material. The decrease in the maximum wear rate occurs at 5 hours DCT with a very significant decrease. It can be concluded that the DCT process on FeAl-MnMO alloys increases the wear resistance up to 65%. The conclusion of our research is the DCT process on the FeAl-MnMO alloy didn't have a significant impact on the microstructure and hardness changes, but significantly increases the wear resistance. In this opportunity, the authors would like to thank Ministry of Research, Technology and Higher Education of Indonesia for financially supporting this research by Hibah Penelitian Terapan in 222. That's all. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.